Okay, yeah. So thanks a lot for inviting me. My name is Alexander Schmidhuber. Most people call me Sasha. Student at MIT, I work on quantum algorithms mostly. I'm advised by Aaron Harrow and Seth Lloyd. And also sometimes I work with Google, and in particular this work was done while at Google. And really what I try to think about during my PhD is what are quantum computers good at? What problems can they solve exponentially faster than any classical approach? And we don't have too many such examples yet. So I'm really, one of the goals of my PhD is to try to give more examples. So I'm going to talk here about sort of one potential way of how to achieve this, which we call Hamiltonian Decoded quantum interferometry, or Hamiltonian DQI for short. And this is joint work with Jonathan Liu, who's a student at MIT, Noah Shadi and Stephen Jordan at Google, and then Alex Paramba and Iwei Kwek, who used to be postdocs at MIT, but now they're both professors. Alex is at BU and Iwei is at EPFL. Let me try to make a laser pointer. Okay. So let me maybe just give like a one slide summary. By the way, please just, if you have questions, just interrupt me. Please ask questions. Okay, let me give a one slide summary of this paper of what I'm going to talk about, which is, you might have seen our related paper from last year, which is optimization by decoded quantum interferometry, optimization by DQI, where we introduced, this is with a different set of authors, but also including Stephen Jordan and Noah Shadi, where we introduce this new kind of quantum algorithm, DQI, which tries to tackle classical optimization by reducing it to classical decoding. And I'll explain more about this in a second. So, this paper got a lot of attention. Ever since we published it, there was a, I would say, obvious question, which is, okay, this is a quantum algorithm for classical optimization. Can you also generalize it to work for quantum optimization? So can it handle quantum cost functions, meaning Hamiltonian cost functions? So trying to find low energy states of some Hamiltonian as opposed to high objective bit strings of some classical cost function. And this is exactly the question that we answer affirmatively in this new paper. So we strictly generalize DQI to the Hamiltonian setting. Okay, so let me start with a brief recap of DQI. I assume you've heard a little bit about it, but I'll just give a recap. If it's too slow or too fast, just let me know. So DQI is a quantum reduction that reduces classical optimization to classical decoding. And this means the following. So let's say you have some classical objective function that you're trying to maximize. And the landscape here typically looks as given in this picture. So there's some global optimum, V, that you're trying to find, but that's generically NP hard to find. So you won't be able to find it efficiently. In fact, even if you try to get sort of a constant approximation ratio, so a constant approximation to that global optimum, generically this is still NP hard. There are these inapproximability results due to things like the PCP, the classical PCP theorem. Either way, you can still sort of try to find the best approximate solution that's accessible to you efficiently. So what DQI does is it reduces this optimization problem to a very different problem, to the problem of decoding a classical linear error correction code. Okay, so the decoding problem means there's some message that passes through some noisy channel, and you're trying to recover at the end what the original message is. So let me be even more explicit here. So this is an instance by instance reduction, which means that if you have any given instance of a optimization problem, so any given specific cost function here, then you can plug this into our DQI reduction, and it will give you a very specific instance of a classical decoding problem. And now you have a guarantee that if you can somehow come up with a classical decoder for this problem, and also someone builds you a quantum computer, which is the harder part, then this gives you, these two things combined, give you a quantum algorithm for the original optimization problem. Yeah.
that's the high-level idea. Now, of course, both these problems are NP-hard. Decoding is NP-hard, optimization is NP-hard. So if you just by itself, this reduction doesn't immediately buy you something. If you want to get speedups out of this, you have to instantiate it with some kind of structure that makes the decoding problem easier. And there are two very natural structures that we study. One is algebraic structure and one is sparsity. Algebraic structure, we give one sort of important example here, which is where the optimization problem, we call it optimal polynomial intersection. So it's essentially polynomial fitting over FP or polynomial intersection over FP. And one can show that this, if you apply this DQI reduction, this now reduces to the decoding problem of a Reed-Solomon code, which are algebraic codes, which have very, very nice properties. They're you can decode them very well and with provable decoders up to very high distance. Now, there's another kind of structure. Sometimes people call this the unstructured setting, which is where you have where the only thing you have is sparsity. So you have a constraint satisfaction problem where the constraints are sparse. And this is very typical. I mean, any max KXOR instance or max cut or traveling salesman, etc., has sparse constraints. The nice thing about DQI is whenever you have a sparse optimization function, then on the decoding side, this means that the parity checks in your code are sparse. So the decoding problem is that of an LDPC code. And the LDPC code, at least if they're random, can be decoded very well as well by message passing algorithms. So this both these structures are sort of promising. We conjecture exponential quantum advantage here in the algebraic setting. In the sparsity setting, we've certainly tried hard to find quantum advantage, but so far we don't have it yet. The issue is that classical algorithms also benefit from this sparsity a lot. Okay, let me instantiate this high-level stuff I just told you with an example, which is the simplest possible example. And again, I'm just explaining now how DQI works, but it will be very useful for understanding how Hamiltonian DQI works. So let's take the simplest possible, or arguably the simplest possible classical optimization problem, which is you just have n linear constraints on n Boolean variables. And you write these constraints as rows of a matrix and some vector. And the goal now is just trying to find some bit string x, so some n bit string x that satisfies as many of these row equations as possible. Okay, so bi is some bit string. This inner product is just a number, which is either 1 or 0. And you force it to be whatever the bit is here in this vector v. Or another way of writing the same problem down is if you want to have some objective function, then a good choice is try to maximize the following function, which counts the number of satisfying constraints minus the number of unsatisfied constraints. Okay, so how does DQI tackle this problem? It reduces it to some decoding problem. So how can we define some decoding problem here? The first observation is that this matrix B, it also defines a code, mainly the code whose parity check matrix is given by the transpose of B. Okay, so a code is just some vector span, like linear subset, and in particular you can write it as the kernel of some matrix. So in this code, there's a natural definition of a decoding problem, which is the bounded distance syndrome decoding problem, which means you have some error E, and you don't know what the error E is. You just know it's syndrome, so the inner product between B transpose and E. And then given that syndrome, you're trying to recover E. Of course, this is impossible in general because the kernel of B transpose is non-trivial, so there are many E's that map to the same syndrome. But now we introduce this additional assumption, which is that E has bounded weight. Okay, so its Hamming weight is bounded by some parameter L. Good. So the central promise or claim of DQI is that if you can solve this decoding problem, up to L errors, up to weight L errors on C-curve, then you can sample from some high degree polynomial in the cost function f of x. And specifically, you can sample from any degree L or degree up to L polynomial in the cost function f of x. And this then allows you to solve optimization, because if you have a polynomial, you can choose your polynomial to be sort of strongly peaked towards large values of f of x, and then when you sample, you will get typically a good solution. Okay, so this was just a recap of DQI. Are there any questions about DQI? Is this all perfectly clear? If not, I'll move on to the main, to the actual content of this paper, which is how we generalize this to act on Hamiltonians. Okay, so there's like a fancy figure visualizing our algorithm, but let me first explain it in simpler terms. So what I've shown you so far is how to reduce classical optimization to classical decoding. Now, it would be nice if this general idea of using a quantum computer to reduce some interesting problem to another interesting problem, if that extended beyond just classical optimization. And I work in physics, so for me, I'm particularly interested in Hamiltonian problems, the problems concerning physical Hamiltonians. And there are a few interesting ones. For example, Hamiltonian optimization, meaning trying to find ground states or low energy states of some Hamiltonian. Gibbs sampling, so preparing Gibbs states at some finite temperature. Or Hamiltonian simulation, so time evolution. And indeed, we answer this question in the affirmative. So we show that all these problems, you can also reduce classical decoding using this Hamiltonian DQI algorithm. But in fact, there's something else happening now. So if the Hamiltonian is commuting, if all the terms pairwise commute, then indeed this is all you get. You only have to solve, you only reduce to a decoding problem, and that's all you have to solve. However, if the Hamiltonian is non-commuting, then turns out you have to solve a different problem as well on top of this decoding problem, which is a certain combinatorial problem on the anti-commutation graph of this Hamiltonian. So anti-commutation graph is just, yeah.
So I just wanted to know that how hard this Gibbs sampling problem is. What is the state of the art?
So it depends a lot on the Hamiltonian. So
okay,
in general, it's, so if you give sample at 0 temperature, that's preparing ground states, and preparing ground states is Q&A hard. So you won't be able to do it efficiently. Even at finite temperature, for many Hamiltonians, it's impossible to efficiently prepare the Gibbs states. Like even if you have a classical Hamiltonian, like a random k-sat instance, or let's say a random kxor instance, then there's some phase transition where above some temperature it's easy, and below some temperature it's hard to prepare the Gibbs state. So it depends a lot on the Hamiltonian.
Right. So if it was a k-local Hamiltonian, then how does it scale with k, the complexity?
Again, it depends on what k-local Hamiltonian you have. So there are easy k-local Hamiltonians and there are hard k-local Hamiltonians. Like a random spin glass is a hard k-local Hamiltonian, and the complexity doesn't even depend much on k. It's just exponential. Whereas,
thank you.
Yeah, there are also many easy classical, like if you have a frustration-free Hamiltonian. Yeah. Okay, so this is already some sort of level of this reduction that's not visible at just a classical level. So this extra problem here that appears, because classical cost functions, they always commute. So you only see this problem. But it turns out there's a richer structure to this idea. And for people who have studied this before, another way of seeing what we do is we generalize what's called Regev's reduction from the abelian setting to the non-abelian setting. So if you've read this DQI paper, then
the core underlying primitive that gives rise to these quantum speedups in our paper is what's called Regev's reduction, which has so far been exclusively studied for abelian groups. In fact, it's usually studied for over lattices, which are special cases. And it's a quantum reduction from sort of two lattice problems. But of course, there are many non-abelian groups that one could be interested in. And one way of understanding our paper is we generalize this Regev's reduction from the abelian setting to a specific non-abelian group, which is the Pauli group. Okay, so before I explain how the algorithm works, let me just compare side by side DQI to Hamiltonian DQI so that you can see what changes. So in DQI, the input is some classical cost function. And let's just assume the input to be discrete. So let's say it's over bit strings. Any classical cost function you can always write as some classical Hamiltonian, so some diagonal Hamiltonian, whose eigenvectors are bit strings. And I just choose my Hamiltonian to be such that eigenvalues on some bit string x is f of x. And in the discrete case, this just means H is a Pauli Hamiltonian that contains only Pauli z terms and no x or y terms. So now we just take the obvious generalization. We look at quantum cost functions. So some functions on some Hilbert space, which are given by arbitrary Hamiltonians. So arbitrary signed Pauli Hamiltonians. Now the PIs here could be x, y, or z term Paulis. And they're bit string, they're Pauli strings. So there are some Pauli operators acting on n qubits with potentially high locality.
What is VI?
So VI is just a bit, which is either 0 or 1. And it defines this phase. So basically, I'm just allowing Pauli operators with arbitrary phases, which could be plus or minus 1.
It's important probably that you have both sides.
So in our paper, we only show how to handle the case where the signs are plus minus 1. But recently, by another paper, it's been generalized. Our algorithm has been generalized to work even for arbitrary coefficients, which are not plus or minus 1. Yeah. So in DQI, as I've said, sort of the goal is to prepare a sample from this classical probability distribution that scales like some degree, the square of some degree L polynomial in f of x. So the natural generalization here is just you want to prepare this density matrix, which scales like the square of some degree L polynomial of H. And this really is the same thing because if you measure this in the eigenbasis of the Hamiltonian, then it gives you some eigenvector with a probability that goes like P of the eigenvalue squared, so P of the energy squared. And indeed, if you identify F with this classical Hamiltonian, then this distribution here is exactly this distribution. So that's our goal. As I've said, in DQI, you reduce this to classical decoding. In Hamiltonian DQI, you get some extra problem as well. The method in DQI is Regev's reduction, or in other words, just a quantum Fourier transform. And the way we write Hamiltonian DQI in our paper, the method we use is what we call coherent Bell measurements. But it turns out that's actually just that's very closely related to the non-abelian QFT over the Pauli group. Essentially, coherent Bell measurements are sort of one subblock of the non-abelian QFT. The subblock indexed by the defining irreducible representation. So indeed, our method is also the QFT, just over a different group. Now, earlier I alluded to how if you have sparsity in the cost function, this also gives you sparsity in the parity checks of the code. And now here on the Hamiltonian setting, we have a very similar, very, very nice, I think, structure preserving property, which is whenever your Hamiltonian is local. So this includes basically any Hamiltonian in the real world. This means that the decoding problem you have to solve is also local. So it's that of an LDPC code.
Okay, and let me say one more very important thing, which is DQI, we only give as applications classical optimization. But if you look here at the stencil matrix that we prepare, of course, you could choose your polynomial to approximate other functions as well. You could, for example, choose your polynomial to approximate the exponential function, e to the minus beta x. And this density matrix here is a approximate Gibbs state. So by just choosing your polynomial in the right way, you can either do Gibbs sampling, or you can do optimization, or you can do many other spectral filters. So for example, you can try to choose your polynomial to be some delta function over some energy, and then what you prepare is a microcanonical ensemble.
So here these polynomials are bounded degree, right?
Yes, so exactly the degree L, where L depends on how many errors you can decode.
And on the right hand side, when you say you can have approximate Gibbs state, then what does it mean?
So if you, let's look at like the exponential function, e to the minus beta x. So you can try to approximate with some degree L polynomial, and the higher L, the better your approximation is, right? And then if you put that in here, this polynomial, then this is essentially e to the minus beta h divided by trace of e to the minus beta h. So it's the Gibbs state, up to some approximation error coming from the fact that the polynomial is just a polynomial.
So how good is that approximation? Because
yeah, good question.
So
good question. So I'll explain it in a bit more detail, but essentially we find that if you want to prepare Gibbs state at temperature beta, so inverse temperature beta, up to inverse exponential error, then you need L to scale, then you need L at least beta over square root of 2. So L has to scale linearly with beta, essentially.
okay.
And if L is above beta over square root of 2, then there exists very, very good polynomial approximations to the exponential function e to the minus beta x, at least in the relevant regime. Okay.
I see.
Because sort of higher beta means lower temperature, so it's harder to prepare. Means right. You have to go to higher L, which means you have to decode more errors.
Right.
Okay. Any other questions about this slide or this high-level overview? If not, I'm gonna talk next about how the actual reduction works.
I wanted to ask something.
Yeah.
So you use this non-abelian QFT over the poly group. Is there any benefit of using, I don't know, thinking of other non-abelian QFTs like over other non-abelian groups? Is there something there interesting?
Yeah, it's a good question. Yeah, so it's something I've worked out, or I've been working on. Sort of, of course, we generalize just to the poly group, and there are many other interesting groups. So what happens if you generalize to those? There are a few very nice properties of the poly group that I'll show in a second, which make this reduction work. And for other groups, the reduction by itself also works, but turns out the decoding problem just becomes very, very difficult to solve, to the extent that the reduction doesn't buy you many nice algorithmic things. So sort of to give a short answer, yeah, there is a lot of sense to it. It's a very natural question. It seems to work particularly well for the Pauli group and not as well for other groups.
Just to be curious, what groups did you try? Or because it sounds like you tried quite a few. So
yeah. So I mean, I have some paper coming out where we discuss a bunch of other groups, but yeah, the dihedral group, the symmetric group, other slightly abelian groups. Other slightly non-abelian groups. Yeah. stuff like that. Yeah. Okay, so then let me explain how this reduction works. And I want to start by addressing what I think is the elephant in the room, and also sort of alluding to the question that was just here, which is decoding is a very abelian problem by definition, right? You can see this by just the fact that it's written in with additive notation. Whereas the Pauli group is non-abelian. So how can you reduce some non-abelian problem here to a abelian decoding problem? And the trick that we're going to exploit is that, so yes, it's true that the Pauli group is non-abelian, but in some sense, it's as abelian as possible. It's very close to being abelian. And you can see this in two ways. One way to see this is that if you have two Paulis, then they either commute or anti-commute. Those are the only two options. Sort of there's only two options, which is either you get a plus or a -1 sign. Another way of phrasing this is that the Pauli group is a central extension of a very large abelian quotient, C2 to the 2n, by just 4 phases. The 4 phases appearing in the Pauli group. And the sort of operational map which implements this projection onto the abelian part is what's called the symplectic representation of a Pauli, which is just a map that takes some Pauli and it rewrites it as a 2n bit string, where the first n bits tell you the location of x operators in this Pauli string, and the second n bits tell you the location of z operators on this Pauli string. And y is denoted as x times z. So if you have some y operator on some bit, you have a 1 on the x part and a 1 on the z part as well. So this symplectic map, it's a group homomorphism. So if you have two Paulis and you multiply them together, then the symplectic maps, they just add together. And now this is fundamentally here an abelian operation already. So even though multiplication in the Pauli group is non-abelian, under the symplectic map, it becomes abelian. So we'll exploit exactly this. In short, what we do is we have to solve some abelian decoding problem on this large abelian quotient. And then we have to do some extra combinatorics to sort of lift it to the whole group. But because this non-abelian part is very small, the extra combinatorics are not very, they're manageable, at least sometimes. Okay, so let me just go step by step through the algorithm now. So our input is some signed Pauli Hamiltonian with polynomially many Pauli strings. And we're given some degree L polynomial, and we want to prepare this density matrix. Now, of course, this density matrix, we're running a quantum algorithm, so the evolution should be unitary. So what we're actually going to prepare is some.
Excuse me. Yeah, can you go to previous slide a little bit?
Yeah.
So Clifford lies somewhere in this symplectic structure, right? So the Clifford group can be like so Clifford group also has similar structure, right? This can be written as symplectic maps. So is Z2n kind of related to Clifford group in some sense?
Yeah, so Clifford group is sort of one higher level here, right? Like Hadamard, etc. It's not in the Pauli group; it's in the Clifford group. Is sort of a higher level.
Yeah, I think it's a bad question. Go on.
No. It's I think it's not directly related, but yeah. Okay. So first we have to, because we can't prepare a density matrix directly, we can prepare a purification of it. So we have to choose some purification that we want. And I'm going to choose this one. Actually, this is the only reasonable choice, which is you prepare a polynomial of H applied to 1/2 of a maximum entangled state. So I just take maximum entangled state means I take 2 copies of the system and I prepare this entangled superposition. And the nice thing about this state is that it looks the same in it looks almost the same in every eigenbasis, in every orthogonal eigenbasis. So in particular, if you look at the eigenbasis of H, which are denoted by these lambdas, then the state looks basically the same. So here lambda bar is just a vector. It's the same vector as lambda, just the coefficients are complex conjugated. So this means that this state here is really a purification of what I want, because if I rewrite it, it's easy to see that it takes this form. And then if I trace out the second register, I get exactly the density matrix I want. So this is, one can think of this in many ways. One can think of, oh, this is just one way of purifying this density matrix. Actually, there are many reasons why this is the right state to prepare. There's representation theoretic reasons that I want to get into, but also this state has many nice properties. For example, if you choose P to approximate the exponential function, if you want to prepare Gibbs states, then this is a purified Gibbs state, which is called the Fermi field double, which has interesting interpretations in quantum gravity and wormhole physics. Okay, so our new goal is, we have the same input. Our new goal is to prepare this purification, this pure state. And of course, it's normalized. So I just implicitly assume the polynomial here is normalized. Okay, so it's a 4-step process of how to prepare this. So the first thing I have to expand this Pauli group in terms, I have to expand this polynomial in terms of its Fourier basis, essentially. So H is some sum of Paulis. So P of H will be some sum of products of Paulis. And I write a product of a Paulis as just Py for some bit string y, where the ones in the bit string y tell me which Paulis appear in this product. And once I do this, I can just re-express P of H as sort of a sum of Py's. And if P has degree at most L, then the Hamming weight of these y's will be bounded by L as well. So this is just a classical pre-processing step that is easy to do. You just re-express your polynomial in a different basis. Okay, then you do the first quantum part, which is you prepare a quantum state whose amplitudes carry these amplitudes in the Fourier expansion of the polynomial. So you prepare a superposition of Dicke states. Each state here is a Dicke states, and you weigh, this one is a Dicke state at weight k, and you weigh it with some amplitude, which is just wk, or omega k. This state is also easy to prepare. And then you just entangle everything with, again, the maximally entangled state. So you tensor everything with the maximally entangled state. So everything here is still easy to prepare. Then the first step you do is, now you apply controlled Pauli operators. Conditioned on the y register, you apply Py to the first half of the maximally entangled state. So this controlled Paulis are easy to implement. You can do this easily. You can also get these phases in here by just doing controlled Z gates. So this is also easy. And now you're almost done. If you could just erase somehow this Y register, then you would have prepared P of H. So this is exactly now the decoding problem. We're trying to get rid of this Y register, meaning we try to set this Y register back to 0. So the decoding or uncomputation problem we care about is, given Py applied to 1/2 of the maximum entangled state, can you figure out what Y was? So can you map Y back to 0? Any questions here? So really the step 4 is the only hard step in this thing.
So where does the particular code comes in here? So you have like some strings which satisfy some properties.
Yeah, very good. So I'll talk about this here. So it comes in when trying to solve this uncomputation problem. So I'll just move on, and then it will become clear where the code appears. So this is the decoding problem we have to solve. How can we solve this? Maybe do people have ideas of how to solve this decoding problem? So you have some Pauli error applied to 1/2 of the maximum entangled state. The Pauli is a product of small Paulis, which you know. Can you somehow recover y? If people have ideas, let me know. I can give sort of a few hints. So the right way to solve this problem is to divide it into 2 steps. So the first is sort of, it looks like a quantum error correction problem where, this is a quantum state. First, you have to somehow, given that quantum state, so okay, what's happening here? You have some maximum entangled state and then some unknown Pauli is applied to it. So you can think of it as like an unknown Pauli error applied to a logical code word. And first you have to figure out what this unknown Pauli is. So you have to recover what Py is. And then once you have Py, you're not done because Py is the product of these like Pi's that are given. And you still have to decompose Py into the small Pi's to figure out what this bit string y is. There are really sort of 2 steps here. Unfortunately, the first step is just easy to do. It's easy to do again because of nice properties of this maximum entangled state. And the first nice property is if you have any 2 Paulis, any 2 n bits Pauli strings, and you apply them to the first half of the maximum entangled state, you will always get orthogonal quantum states. And this means that information theoretically, this problem is solvable because all these for different Paulis, this is always a distinguishable quantum state. And then moreover, it's also efficiently possible. There's an efficient measurement which reveals what this Pauli is, which is just a Pauli measurement, the Bell measurement. If you measure the state in the Bell basis, then you get 2n measurement results, right? So you get a syndrome of length 2n, of 2n bits. And it turns out, this is maybe not obvious, but it turns out that these 2n measurement bits, they just exactly equal the symplectic representation of the Pauli.
So it seems like other groups will fail on the step 1 because here you get orthogonal states. If I change the group, then probably it will fail here only.
Sorry, I didn't hear your question acoustically. Can you repeat it?
I was just thinking that since Pauli gives you orthogonal states, so you could like distinguish different states corresponding to different y's. But if I choose some other group, then probably this property will fail first.
Yeah. Actually, I think that's a very natural thought. Actually, what you can do for other groups, for general groups, is you just operate over sort of the formal span of the group elements. So you just define each group element to be an orthogonal vector in some abstract Hilbert space. And then you can also get this problem, this property that sort of different group elements map to orthogonal states. But then you have a problem which is you don't have an efficient measurement that recovers this. So sort of information theoretically is still possible, but it's not efficient anymore in general. Yeah, good question. Okay, so step 1 is easy. So then let's look at step 2. So we already know what the symplectic form of Py is. So our new goal is to recover y given that. But this is now just a simple linear decoding problem because the symplectic map is, so the group homomorphism into some abelian quotient. If you take the symplectic map of a product, you just XOR together the symplectic maps of the constituents. So in particular, simp of Py is just a sum of simp of Pi, meaning this syndrome here is the sum of like the syndromes of the Pauli's Pi. So you can just re-express this problem as like a bounded distance decoding problem on some code whose parity check matrix is given by this matrix here. So 2n by n matrix, where each column is the symplectic representation of one of the Pauli's. And y is some
then Y has Hamming weight L, and if you apply Y to this matrix, you just get the sum of the symplectic representations, which is the symplectic representation of the product. So this is how the code enters. You have to, in step 2, you have to solve a bounded distance decoding problem on a code whose structure is defined by the Hamiltonian, because it defines these columns, so it also defines the code. And by the way, if your Hamiltonian is diagonal, so it only contains C terms, then only the first n bits of the symplectic representation are non-zero, right? All the x parts are 0. So then you can just truncate this matrix and get an n by m matrix, and that's exactly the same matrix as you get in DQI. So again, we give a strict generalization of DQI. Okay, so unless there are questions here, I'm going to move now to the code which I've skipped, which is, here sort of implicitly I've assumed that the Paulis are commuting, because when I wrote down this product, I didn't care about the ordering. I just ordered them in some canonical way. And of course, in general, that's not true. And unfortunately, that makes things much more complicated. So just to give sort of the upshot in a short way, what happens now is that if you expand this polynomial of H, there will be now many cancellations. So for any given set of k Paulis, you can reorder them in k factorial many ways, and you will always get either plus or minus sign. So in the end, you get sort of an average sign averaged over all reorderings, which will be some number that's between -1 and 1, arising due to cancellations. And if sort of the only thing that you have to modify in this whole routine, you only have to modify step 2. You only have to change which pilot state you prepare. Everything else is just the same. And in particular, you have to replace the pilot state with now, it's not just a weighted sum of Dickey states. Now there are weights, varying amplitudes even within the Dickey state. So each Y has now its own amplitude, which is exactly sort of this average sign that you get from permuting the Paulis in the bit string Y. So this state, unfortunately, it seems very difficult to prepare. And what we show is that, nevertheless, so even though it seems very difficult to prepare, we show that you can always express it as some matrix product state with linear bond dimension, defined on local sites given by the connected components of the anti-commutation graph of the Hamiltonian. So anti-commutation graph just means we make one vertex for each term in the Pauli, one vertex for each term in the Hamiltonian, and one edge if they anti-commute, and no edge if they don't anti-commute. And what we show in this theorem is that if the anti-commutation graph is very sparse in the sense that the largest connected component of the anti-commutation graph has size log n, where n is the number of vertices, then we can efficiently prepare this pilot state here using a matrix product state preparation algorithm. The idea is essentially sort of as I said, the site dimension in this MPS representation is 2 to the d, where d is the size of the connected components in this graph. So if d is only size log n, then this is a polynomial site dimension, and then you can prepare these MPS states in polynomial pair. Okay, but this is really sort of one big open question is, can we prepare this pilot state for more general Hamiltonians? Right now we can only do it if the Hamiltonian is very close to commuting, in the sense that the anti-commutation graph has small connected components. Okay, how am I doing on time? I have, I guess, a few more minutes. So
yeah, no, you have a lot. There's like we had an hour and a half. Yeah. So you can go as slow as you want. Don't worry about it.
Okay, I'll spend like another 15 minutes, I think. So let me get now to the interesting part, which is
what can you actually do with this algorithm? What are its applications? So the first thing you have to do, and we've talked about this a bit earlier, you have to do some simple Fourier analytic calculations of, okay, let's say I want to do optimization, or let's say I want to prepare Gibbs states. What's the optimal degree L polynomial I should choose that will solve this task in the best way? And we just answered these in our papers. So we show that, if you want to maximize the energy that you get, the average energy you get when you sample the state, then there's some specific polynomial that you should choose for any given L, which we write down implicitly in our paper, and it will achieve the following approximation, the following energy. So it will achieve some energy which scales like a semicircle in L, where L is the number of errors you decode.
So sorry, you are optimizing energy here.
Yeah.
You are minimizing, or?
Yeah. Okay. I mean, it doesn't really matter. I've written it here as optimizing, but of course you can replace H with minus H, and then it's minimizing. So
this is maximization. Okay.
Yeah. So here I'm writing maximizing just because then it's easier to compare to DQI, because in DQI we try to maximize the objective function. But you can always replace the Hamiltonian with minus the Hamiltonian, and then maximizing the energy becomes minimizing the energy. So computationally, it's the same problem.
Right. So this is like, in some sense, ground energy estimation.
Yeah, exactly. So this is ground energy estimation. Yeah. You can just invert these scales and think of one as being the ground state energy, and here being the highest energy, and then we get closer and closer to the ground state energy as L increases. This is, by the way, the same form as in DQI. And the second question is, okay, let's say you want to prepare Gibbs states. And here we prove this theorem I alluded to, which is if you want an exponential small error at temperature beta, then you need L to choose scaling linearly with beta. Okay, so now, these are just some like sort of steps you have to do first to just understand how the algorithm works. But now let's look at specific Hamiltonians. So again, we should enforce some structure, and we could enforce sparsity or algebraic structure. Now we have a second knob which we can turn, which is the Hamiltonians could be either commuting or non-commuting. In the commuting case, we don't have to solve this pilot state problem, so that makes it easier. Okay, so we just give one example in each of these areas. So the first thing we study, the simplest thing, is a random local commuting Hamiltonian. So we randomly choose some local Hamiltonian, so local terms in a Hamiltonian in a way that they're commuting. And now the decoding problem you get is that of a random LDPC code, right? It's LDPC because the Hamiltonian is local. And random LDPC codes you can decode very well with belief propagation. So HDQI does, so then we try to prepare Gibbs states or prepare low energy states. And we can compare it to classical algorithms. And
so
what we find is that
when you say, sorry, in this case, when you
ahead.
say local, do you mean one local, or is
I just mean constant locality. Yeah, K local. So
okay.
I think it's 4 in our case. I'm not sure. We study different localities, like 4, 5, 6. Okay, so unfortunately, as in a classical case, in the sparse, if you only have sparse structure, we don't find quantum advantage. What we do find is that HDQI gets close to sort of the best energies achieved by a classical algorithm called simulated annealing, but we don't beat it. There's sort of a technicality we could say here, which is if you want to prepare Gibbs states, then HDQI can provably prepare Gibbs states, whereas simulated annealing usually does not converge to the Gibbs distribution. So at least at finite times. So in some sense, we can prepare Gibbs states provably, whereas SA cannot. But I don't want to sort of put too much focus on that part. Okay, the next commuting model we study is now, let's add algebraic structure. And here what we study is preparing Gibbs states of stabilizer code Hamiltonians, like Haah's fractal code, or the 2D toric code, or the 3D toric code, etc. And for Haah's code and the toric code and many other codes, we show that HDQI can provably prepare Gibbs states at any temperature, even temperature scaling exponentially in system size. And these were some new results, but in fact, what we also give in our paper is we give a classical algorithm that also achieves all of this. And then there are some non-commuting applications which are more interesting, and I'll talk about them separately in a bit. Let me. Okay, so here, actually, what I have now is like one slide for each of these blocks. Yeah.
Sorry, just quickly so now I'm a little bit curious about the efficient classical algorithm. So are they motivated by the quantum one, or are they just like you found some entirely different approach to solve the problem?
They were different. They're not motivated by the quantum one. Actually, Noah Shadi came up with them. And the algorithms are actually very simple. So it's in some sense like a more sophisticated version of rejection sampling. So if you have, I'll say a little bit more about it on one of the slides.
Yeah. Sorry. Yeah. Okay. Of course.
Yeah. Let me just give a bit more detail on each of these blocks now. So in the random commuting model, it's not too important what's written here, but I just want to sort of compare energies. So here we give the maximal energy in percentages achieved by HDQI, and we compare it to some classical algorithm that we come up with. And the classical algorithm consistently outperforms HDQI. But they're sort of, they're not too far apart. Oh yeah, I should mention another very important thing which I didn't mention, which is a nice thing about this reduction is, even though it's a quantum algorithm, you can actually run it, you can predict its performance numerically by just looking at the classical decoding problem you get, and you can run your best heuristic classical decoder on it for very large sizes, for like, 10,000 qubits or 100,000 qubits, because it's just a decoding problem on 100,000 bits, which you can do easily. So you can actually, for very large system sizes, predict the performance of HDQI. You just run your decoder, see how well it does, plug that number L into your theorem, and then you know how well the quantum computer would behave if you had it. Okay. The second sort of square I talked about are structured commuting Hamiltonians. And here sort of our main insight is that if the code is a very good code in the sense that it has only a constant number of code words in it, so the dimension of the kernel of this matrix is constant, then HDQI efficiently prepares any non-zero function of the Hamiltonian. So any positive non-zero function of the Hamiltonian. And there are actually many examples that satisfy this property, including sort of most topological quantum error correction codes. So for one example, the simplest example is the toric code, where there are only two code words in the toric code because there are only two relations among the stabilizers in the toric code: the product of all plaquettes and the product of all star apertures equals 1. So the toric code satisfies this condition. We can prepare Gibbs states at arbitrary temperature. But the same is true for all these Hamiltonians here. So I'm not going to talk too much about them. And preparing Gibbs states at arbitrary temperature for these Hamiltonians has been a topic of recent interest. So there are a bunch of papers that sort of give the first, or seemingly the first, efficient protocol for preparing these Gibbs states in polynomial time.
And HDQI subsumes these results, or many of these results. We also do it for many of these Hamiltonians studied in these papers. But as I said, we also give a classical algorithm. Noah Shadi gave it. And here the idea is essentially rejection sampling, and we'll exploit that the dimension of this code is very small. So one can show that preparing Gibbs states of these Hamiltonians is equivalent to sampling syndromes of this code at uniform Hamming weight, which is at any fixed energy. And essentially, because the code has so few code words, you can just uniformly send in arbitrary bit strings and then check if they are syndromes and then post-select. So roughly that's the idea behind Noah's algorithm. Okay. Now, the more interesting case is non-commuting Hamiltonians. Again, we have this theorem that if the pilots, so now we have to prepare the pilot state, which is very difficult in general. But if the anti-commutation graph has only log n size components, we can do it efficiently. So we give two applications. The first is what we call a semiclassical spin glass, which is sort of a interpolation between a classical spin glass and a quantum spin glass. So it's a classical spin glass where we flip with some constant probability p, we flip the z terms in the Hamiltonian to x terms. And one can show that if this probability p is chosen constant but small enough, be very few x terms, so there will only be few anti-commuting terms, and there's some percolation threshold where below that threshold the anti-commutation graph will sort of factor into small components of only log size. So below that threshold, we can prepare this guiding state, so this pilot state, meaning we can also, because the decoding problem is also again an LDPC problem, we can also prepare Gibbs states of this Hamiltonian at some constant temperature. And now here there's no classical competition because it's just a purely quantum problem. You can't diagonalize this Hamiltonian with Cliffords, for example. And then we do the same trick for destructured Hamiltonians. So we start with some algebraic Hamiltonian like a toric code, 2D toric code, and we just add random defects. So we replace some of these operators with, we swap like c to x or x to y, etc. And this way you also get a non-commuting Hamiltonian where we can prepare Gibbs states up to some finite constant temperature. Okay, so I'll end here.
Sorry,
I want to highlight
in the last slide. Sorry, before you summarize. So in the last slide here, do we know what the state of the art for classical algorithms is? So
you can't really even talk about a classical algorithm for preparing these Gibbs states because it's a purely quantum problem. Sorry?
For instance, sampling from the Gibbs states for these Hamiltonians, is that already covered in the previous? Because I thought in the previous slide they were all for commuting Hamiltonians, right?
Yeah. So in the commuting Hamiltonians, what do I mean when I say you can do this classically? So the bits if you sample from it, the vectors are quantum states, so you can't really sample from it classically. But if the Hamiltonian is commuting, then there's some Clifford that diagonalizes it. So you can write these quantum states as in terms of like a stabilizer description. So then you can
So
classically sample stabilizer descriptions. Yeah, exactly. There's an efficient description of them. Whereas here in general, there won't be any efficient. Yeah. You could still, if you wanted, you could still talk about energies. So you can still say, maybe you have some classical algorithm that predicts the ground state energy. And there we tried to play around a bit with perturbation theory, but we couldn't find a classical algorithm that achieves what our quantum algorithm achieves.
Right. Okay. Thanks.
Okay. So let me end on some future directions. So I think the most important one is right now we're quite bottlenecked by preparing this pilot state. So it's a very strict condition that the anti-commutation graph has these small components. And it would be very nice if we could prepare it for more interesting Hamiltonians as well. So maybe for less sparse graphs, or maybe there's even structure, and in fact, I think so. Maybe there's structure in the anti-commutation graph beyond just sparsity, which also allows us to efficiently prepare this state. So those would be very useful questions to answer. And of course, the general question is sort of, yeah, what Hamiltonians should we study? So what are good, interesting quantum Hamiltonians, which are classically hard, but under this reduction correspond to good classical codes, such that our quantum algorithm works well. Okay, thank you very much for listening.